David Bowie's Under Pressure. We all know it, we all love it. But do we all know it? Because let me ask you a better question. How much pressure was David Bowie really under? For that matter, how much pressure is anything under? Well, one dude thought about this for a while and said if only there was some way to correlate pressure with, say, temperature, something easy to measure. Well, that man was Antoine, and he gave us this equation, which relates the pressure to the temperature, where the log base 10 of the pressure is equal to some constant A minus some constant B over some constant C plus T. Cool, excellent. That's a lot of constants, and I don't know any of them. Well, there are ways we can find them, but I'm afraid we're going to have to use math. Now, before you go crazy, let me assure you, we have machines that can do the math for us. The only thing we need is a nice set of data we can use to build a model, some sort of equation that we can use to get the actual A, B, and C. Now, we'll do something simple. Water. Where would we find data for water? Well, over here we have the Dortmund database, which has lots and lots of data on lots and lots of things, including relating the temperature and the vapor pressure of water. Now, that's all good. I don't want to have to do all this by hand. That's where code comes in. So, we're going to get a nice clean sheet of Python, and we're going to import some things. We're going to import HTML here. We're going to import requests. We're going to import NumPy. We're going to import some stuff from Plotly. In this case, it is make subplots. And from SciPy, we will import minimize. And we'll shift enter and import everything. Excellent. Now, with the power of HTML, we can do a fun thing of pulling all the data from the website. But there's one side problem, and there's the Dortmund database doesn't like HTML scrapers. So, I'm giving it a huge shout out to Professor Ko and his gaming chair because he prepared this. A complete HTML copy of the Dortmund database that just has all of the data here we can use. Well, I can use. So, in this case, we're going to set our URL equal to this. I'm sure you didn't want to see me type all that out. We're then going to do content, and we're going to say get requests. Can I get this URL and then give me its content? And I'm going to make the HTML tree as HTML from string, and I'd like to see the content of it. So, what is in tree? An HTML element. Excellent. What is in content? A whole lot of HTML that I'm sure no one wants to read. So, we're going to have to go, and we're going to get the strings of the temperatures, because that's what we're interested in here, are those temperature values on the far left. And we're going to say, we're going to use tree.x path, and we're going to get this whole fun bundle of stuff. What does any of that mean? Well, these double slashes means it can just go and it can keep digging into any elements it needs. We've got some wildcards going on here, and we're looking for specifically anything tagged ID online Dortmund database form. Something like, say, I'm sure we've got Dortmund database form around here somewhere. Well, it's in there somewhere. You may spot it before I do. I don't think I have the time or the patience to try and spot it. So, but it's in there. And we're going to look for the second divider, the third table, and we're going to go in the table body, which here's our first table, and here's our second table. We're gonna dig everything up from this second table. And those TRs, those TDs, we're gonna say I'd like everything that doesn't yet have a position that is not third or greater in the table. So state and reference we don't care about. What we want are these temperatures and these pressures. So that's what we should get. So we'll run this and we'll ask what is T-strings. And excellent, we now have a usable array. Well, we have a readable array. With the problem is, as you may see here, they're kind of stuck together in a funny way. We've got a temperature and then a pressure, and then a temperature and a pressure. That's not fun for a machine to read. That's not fun for me to read. And while I may struggle with basic tasks like a zipper, the machine doesn't. So we'll say we want some data. We'll make a list, and we'll say I'd like to zip something. We'll take it. We'll put two things. We'll stick them together, and let's say we want T_strings or temperature strings. Now we want every other item, so we'll want to go into our syntax for that. We'll say I'd like, starting from the beginning, going to the end, and every other item. Now we'll zip it with itself. In this case, I'd like, starting from 1 and then to the very end, again, every other item. So now, what is data? Something I apparently can't type. We now have a list of arrays. Well, that's progress. It's still all in strings, but it's at least in a shape we want. So from here, we'll go, we'll set it back to itself. I can't be bothered to make more variables. NumPy, our secret tool. It's not very secret, we all know and love NumPy. I'd like an array, please. And we're going to have to make it so it writes itself. And we're going to say, I would like that the variable T and the variable P vapor for vapor pressure. Then I'm going to write a for loop so I can iterate through item T and item pressure vapor, which will then be written back into this little array there. And I'd like it from, we'll do the same thing. We'll do zip, and we'll just copy this. And that's where I'm pulling it from. But then there's one slight problem with all this, and that is that's not going to give us a list of strings. We don't want strings. We can't do math with strings. The machine can't do math with strings. So we're going to do an as type, and we'd like numpy's double precision floating point number. Let's run that, and now let's look at data. Well, it's now a numpy array. It's all in double floating point precision numbers, and it's now all in a shape we'd like it to be. We've got our temperatures and we've got our pressures. Excellent. With this, we can actually get something done. Now, we're going to go ahead and we're going to go and make two sets of lists here from our one set list. We're going to go with temperature, and we're going to go log P, because as you remember, we don't want the pressure, we want the log base 10 of the pressure. So we'll send it to data, and I'd like the entire thing, but only the 0th column. And that's going to be all of our temperatures. And then the other variable we're going to positionally assign here to save some lines. We're going to say numpy.log10. Don't be like me and try and confuse log10 and log. Log is your natural log. Log10 is your normal just log. So there's you can make some mistakes and accidentally put in the wrong log. Make sure you know what tree you're cutting. And we'll say 1,000 times the same data, but in this case, I would like the whole thing again, but this time the first column. Now, why the times 1,000? Well, it's because this entire thing is written in kilopascals, but normally we kind of want all our math done in regular pascals. There's nothing stopping us, because we could just get an A, a B, and a C in terms of that, kilopascals instead of regular pascals, but it's more traditional to use pascal. So we'll follow tradition, and we'll just run that. So now if you look at T and log P, I will do T. We're going to see we've got a nice array of all the temperatures in degrees Celsius, and log P, we'll see we have an array of some interesting looking numbers, which are all just the log base 10s of the vapor pressures. So, what do we do with this? Well, we're going to make a pair of functions. We're going to define a function. We're going to call it Antoine, because that's what it is. It'll need an A, it'll need a B, it'll need a C, and it'll need a T, a capital T. It doesn't really matter, but I am a stickler for consistency. And we're just going to return an equation defined as A minus B divided by C plus T. And that, of course, is going to be our equation from back there. Now, we're going to make a second one. We're going to find a sum squared error. What does that do? Well, that takes the errors, or how far off all the data is from where it thinks it should be. So we can just kind of guess an A, a B, and a C, and we can run them all together. Attempt to run it through Antoine and see what does it spit out. Well, if we somehow magically guess A, B, and C correctly the first time, the sum squared error, which is to say how far apart of the number each point is from the actual data point squared so that the sums don't cancel each other out and so that really big errors are incredibly obvious. If we somehow guess the right numbers, that'd be pretty much 0. We won't guess the right numbers. So instead, we'll use the sum squared error to say how far away were our guesses from the actual guess. You're probably wondering, why have I only put one side for vars if we're going to, of course, need A, B, and C? Well, that's for a bit later. Unfortunately, the way SciPy works, it doesn't like having, it only likes one slot in it for variables, so we'll have to pass all the variables as one item, but that's fine. Antoine, and we'll say vars item 0, that'll be A, vars, no, not cars, wrong band for David Bowie here, vars 1, and vars 2. Oh, and T, of course, the most important thing, the variable we actually know. And we're going to put out a sum squared error, we'll just call it squarer, something catchy, and we'll say numpy.sum, and we'll put a parenthesis here, and we'll say log P, that is what the data point actually says it should be, and we'll take out what we think it should be based upon our model, and we'll square that. And that is our sum squared error. And then we'll return said squarer. Alright, and we'll go ahead and define these equations. Now, we're going to go ahead and we're going to guess an AI, a BI, and a CI of, let's say, 200, 200, and 200. I don't know what I'm doing. I'm guessing numbers. I know what I'm doing. These shouldn't be anywhere near those numbers, but it needs something to start with. So, with this, what we're going to do is we're going to test out how does our Antoine work. So, let's say we go ahead and give it, we'll run a plot. We'll say, I'll say fig 2, because we want a better figure later. So, we'll make a second figure first, and we're going to go make subplots, that's why we brought it up. And then we're going to go ahead and fig2 dot add. Well, I don't want to type all that. Let's run that. Oh, they didn't like how I've written it. Probably because I forgot an equal sign. Rookie mistake. There, happy now. And so we'll pop a line and we'll say fig2 dot, yeah, that fig2. Add a scatter, please. And we'll say our x is going to be equal to r. T. We'll say our y is going to be equal to our model. It's not called model. It's called Antoine of AI, BI, CI, and T. But then we're gonna copy this line, duplicate it. Oh, and I should probably mention we'll want this one. We'll go ahead and put in mode of this being our model. I'd like this to be a line, and for this other one, I'd like mode to be in just the markers, please. Oh, and for this one, we actually don't want that. We want log p, our actual data. So, let's see how good our initial guess was. I'd say it's not very good at all. I would not say we have a very good correlation here. Okay, so I think we've got some work to do. That's fine, that's fine. That's why we have our secret weapon. We'll make an item called result, and we'll say, I'd like to minimize something, make it real small, real itsy bitsy. What am I minimizing? Well, the function we'd like to make to 0 is sum squared error, or how wrong our guess is. I'd like my guess to be as correct as possible, which means as little wrong. And let's start our initial starting point as, we'll make it an array of AI, BI, and CI. That's why we've got those 3 slots. And then finally we need some arguments, and those will be its base data, t, and log p. And we'll run that, and it did something alright. So, what is in result? Result. Nope, I don't want to be that aggressive. Just a regular result, please. It had success and spit out 10, 1756, and negative 36. None of those I'd say are particularly close to 200, so, you know, what did I say? We're not going to get a first try. And as you notice here, it says x is equal to an array. Well, that means you probably want this x value, whatever it is. Well, good. In fact, x is of type an ND array. We can work with arrays. Well, it doesn't tell me what exactly is in that array, but that's fine. So we're just going to go, I'm going to print the line. I've already got this print line prepared. So we'll just see what is in here. Oh, and we'll want to go A and B and C, the actual ones, don't forget the equal sign, are equal to said array. Well, now we've got something. We've got an A, we've got a B, we've got a C, and we can work with all of them. So, for this, let's make a second pile of temperatures. Oh, not yet. Let's go fig, just regular fig. But the same, make subplots. And we'll run it. Then we'll come back in here and we'll say, I'd like to add a scatter plot, please. Yep. And we're just gonna kinda, I don't really feel like writing all these lines again. They're not fun, so you won't be missing much if I copy these. We'll say, I'd like to add a scatter plot. Oh, let's see what this looks like. Well, there is our data. All those points. And let's look at here. Oh, the first one should be at 293 and at 2.4. Let's go into 293. Oh, right, of course. It's not going to be 2.4. It's going to be the log of 2.4 times 1,000, which I don't know that off the top of my head, but apparently it's 3.38. I'll trust it. It would be around 2,000, and that's going to be around 10 to the third. So yeah, that checks out. Okay, so let's go ahead and add in our model. Was it really as good as it said it was? Did SciPy really minimize that sum squared error? No, because model is an equation. Right. It's Antoine. Let's actually use the correct thing, and let's see what it does. Well, look at that. It seems to have matched up quite nicely. Although, I'm not really liking this straight line. If only there's some way to make it a little, you know, more curved and not this awkward jump. Because there is an awkward jump in the data here, where it goes from, 343 to 412. Well, we don't have any data for where that should be, but we can guess. And we're gonna, now we're gonna make that second copy of temperature. We'll say T2. And we'll say it's equal to numpy dot lin space. That's linear spaced. The number of variables between the start and the stop point, and we'll just let it to be number 50. So that seems good. We'll say a minimum of t, and our stopping point would be the maximum of t, and yeah, num50 is fine. And we'll go ahead and spit out and see what does T2 do in the end. Well, that's a nice array of temperatures. So, why have I made the second copy? Well, we're going to add a third line to our graph, and we're going to go ahead, I'll fix that name up, and we're going to use this finer data, and we'll run it, and we'll now see we've got a nice blue curve here that says, if we just kind of guess wherever the point should be, and if we've got something that say, some 365 degree, whatever it is, well, we know that that is going to be 365 degree steam, probably. That's like what? 100 some Kelvin Celsius? I hope it's more than 100 some Kelvin. 100 some Celsius. That's probably going to be steam at that point. So it's got, 4.8. That tells us it's got at least 1,000, approaching 10,000. What was the unit? No, 10,000, approaching 100,000 of kilopascals. Pascals, which would be approaching that 101.325 kilopascals of atmosphere. and that is indeed what the data here seems to confirm is somewhere in that range. It'll flip to steam. Doesn't want to quite say where, but that's fine. We can say it's somewhere on there. You know, if we were to go further, we could, but for this, we now have a basic model that shows, hey, given this random bunch of data with all these numbers, just from the raw HTML, we can get A, B, and C. And we can tell from this that A is around 10.21, B is around 1756, and C is around negative 36. And just like that, we can tell for any roughly decent number of given temperatures, we can see about what pressure the water would be at. Because what to do is then just say, well, let's go ahead and say, please give me, I will go ahead and make a second one here, and we'll say, press. And we're going to set it equal to T, no. We're going to set that equal to this line up here, the Antoine, and we'll say actually I would like that 10 raised to that power, and let's look at pressure. Well, we can now see we've got our pressure in pascals. And if we just say make a second one, I'm just going to roughly gather this and do that. Well, we're going to call this fig 3 and fig 3. And we run these. And let's go ahead and make that, not Antoine, but let's make that our press, because that's, you know, just a transformation of that. And we run it. Well, we can now see that here at, say, wait, let's make this easier to read. T2 minus 273.15. That'll give us it in nice, tasty degrees Celsius. Which tells us that at, say, 100 degrees Celsius, a little over. We were not quite 100. We've got like 99. We're at, what is it, 97,000? Yeah, 97,000 pascals, or in a nice kilopascal. We'll go ahead and make that pressure divided by 1,000 so we can get it into kilopascals. Well, we can now see at 99 it's going to be around 97 kilopascals, just shy of atmospheric pressure. It's almost boiling, a little over its boiling point at 106 here. It's indeed over that 101.325. And this now means that with nothing more than a pile of data, a simple equation, and a sum squared error that lets us see how far off our guess, how wrong our guess is, we can now tell that for pretty much any given temperature, we've got a pressure. At least for water. Now, all we need is, of course, the dormant data bank to finally give us that data we've been wanting. What is the vapor pressure to temperature correlation for David Bowie? Because until then, we can never really know just how much pressure was he under. I guess that's their secret.